Hey, how's it going everyone, and welcome back to another video. In this video, we're going to walk through a real-world example of using neural nets. And so in it, we're going to classify images of rock, paper, and scissors using a convolutional neural net written in Tensorflow Keras. This is kind of a follow-up to my previous video on neural nets, so if you haven't watched that, I definitely recommend checking it out. In it, we walk through a lot of the kind of background information on how neural nets work and writing some simple ones from scratch. This video also can work as a standalone video though, so don't feel like you have to watch that one, but we might move through some of the things a little bit quickly. All right, to get started, I recommend opening up a Google Colab file. So if you go to collab.research.google.com, you can open up a Jupyter notebook there. And it's kind of nice that we can do this in browser because we can make sure that we all are running the same kind of system. All right, the first thing we're gonna do is install some libraries that we need. So let's go ahead and do in our Google Colab file, do a pip install of, make this slightly bigger, of TensorFlow and TensorFlow datasets. And I'm going to run this with the -q so we don't see as many logs as we normally would to kind of keep this notebook a little bit cleaner. And the next thing we're going to do while that runs is we're going to now import the libraries that we're going to need in this tutorial. So import necessary libraries. And so we're going to be using TensorFlow and Keras specifically, but we'll also be using some other helper libraries like NumPy and matplotlib. So let's import all of those. So import matplotlib lib.pyplot as plt, import numpy as np, then we'll import TensorFlow as tf, and we'll import TensorFlow datasets as TensorFlow ds, tfds. And then finally, with TensorFlow 2, one thing that will be helpful is just to specifically import the Keras library. So from TensorFlow, import Keras. The next thing we're going to do is I'm going to show how we can find data sets for whatever sort of neural net project we want to do, or maybe any sort of general kind of machine learning project. And I think there's a couple, there's all sorts of places you can look for good data, but one thing that I find very convenient is that TensorFlow has a bunch of data sets built into their library. So if you go to either of these two locations, you'll be able to find some data sets that you can use. But we can also see these data sets very easily with tfds.listBuilders. If we run that method, you'll see all of these different lists here. And so when I was prepping for this tutorial, I ultimately did this, and I kind of looked through what they offered by default here, and I kind of kept scrolling. The thing I didn't want to do here is I feel like everyone does tutorials on MNIST and the fashion MNIST. So I wanted to do something a little bit different than the MNIST, which is classifying images of digits with a CNN or with a neural net. So I didn't want to do that. So I kept looking, and ultimately I found this data set called rock, paper, scissors. And I thought that sounded pretty cool. Let's see what it's about. And so let's load that data set in. So the first thing we can do is we can get some information on the data. And to do this, we can use the TensorFlow datasets builder to load in some information about a specific data set. So we're going to do builder equals tfds.builder, and then we need to take that example that we saw up here. So that was rock, paper, scissors with underscores. So I'm going to just copy that real quick, paste it in, and then there's this nice convenient method on builder, which is builder.info. It will load in all sorts of information about the data set. And then if we just go ahead and print that out, we'll see some information about the data set we're working with. So rock, paper, scissors, images of hands playing rock, paper, scissors game. That sounds pretty cool, and it sounds very like appropriate for a neural net tutorial. So what do we have here? Well, we have images that have 300 dimensions, height of 300, width of 300, and 3 color channels. So that means it's an RGB image. We can learn the data type here, which is a uint8. So what that ultimately is telling me is that these are numbers, each of these images are numbers from 0 to 255. And then we also have the class label, which is just a integer that's basically representing rock, paper, scissors. Then finally, another thing that's helpful here is that it gives us some information about the splits. So we have 2,520 images that we can use for training, and then 372 that we'll use for our test set and our validation. And there's also a URL to learn more about this data set. So that's useful. We can definitely utilize this, but let's continue onward and start prepping the data. So okay, and to do this step is kind of specific because we're using the Tensorflow datasets library to do this. Really, the same process is done with wherever you're loading your dataset from, but specifically because we're working with TensorFlow datasets, the way we're going to do this is TensorFlow datasets.load. And now the name is going to be equal to rock, paper, scissors, that same file that we saw before. And the other thing we're going to access here is, and if I actually look at this class method, you'll see some information I can get. Split is the next keyword, and that's what we're going to grab here. We want to separate our training data and our test data, so we're going to say split equals train here. And then for the other one, for our test data, we will do the same thing. But this time our split will be equal to test. And that matches up with what we found when we looked up the information on this data set. So we can go ahead and run that. And one thing I will note is that there's an additional option we can add to one of our previous cells if you don't want all of this information to pop up and kind of mess up the neatness of our data set. And we can go ahead and pass in, when we imported the library, if we passed in disable progress bar, what we'll see when we run that again, and I can show you that, tfds.disable progress bar. And when we run this command again, instead of seeing all of this, these bars and all of this extra information, it'll just run neatly. Okay. So now we've loaded in our data. I think the next thing that's going to be helpful for us to do is actually see some examples of what we're working with, because it's really hard to start writing a neural net unless you've actually seen some images. So let's go ahead and show some examples. And so with the TensorFlow datasets library, we can do this as follows. We can do TensorFlow datasets.show examples. And this is going to be using two things. You're going to have the dataset info as well as the specific dataset. So the info we loaded up here with our builder. That's the info. And then we can either use dstrain or dstest to use as the actual dataset in that method. So we have info and then we have dstrain. And really, again, like, we're doing it a specific way here with TensorFlow dataset, but oftentimes the same process, no matter how you're working with your data, it's good to kind of follow and just get a feel for your data before you start trying to build a model around it. Okay, so this is what we got. You see that they're hands doing rock, paper, and scissors. And one thing you might notice about these hands is that they're some of them are a little bit funky looking, like this one right here I'm looking at. And that is, I remember looking into the data set a little bit. I believe these are all artificially generated images of rock, paper, and scissors. So they're not actual images as far as I know, but they work the same when we're kind of going ahead and training our network. We can kind of utilize them as we'd use a real image. But here, yeah, here's what we're working with, and they have the labels: 0 for rock, paper is a 1, scissors is a 2. All right, we have the examples. Now let's do a little bit of additional data prep. At this step, this is really kind of for any sort of image classification task. I would say this is a pretty similar type of processing I would probably do, but we're basically converting the TensorFlow datasets format into a NumPy format that's a little bit more universal, a little bit more easy to work with, in my opinion. So that's what we're going to do in this next step. I thought the easiest way to figure out how to do this was to first look at the documentation for the datasets library within TensorFlow. So I went to tensorflow.org/datasets/overview. And in there, it told me how to iterate over a dataset, and that's what we have. And the key insight I saw here was that in the dataset, there's images and labels. So those are the two items that we really want when we're breaking up our data. So if we iterate over the examples in our dataset, we can grab those things. And to make it a little bit more concise, let's do that in the form of a list comprehension. So we're going to say our train images are going to be equal to example, and then we're going to use get the image for example in the data set. And that's basically all we have to do. I guess we could run this real quick and see what happens. Oh no. Oh, dataset train, sorry. This might take a second to run. Okay, so let's just look at the first image in there. And let's just get the type of that. So this is a TensorFlow tensor. So what I want to do instead is grab it as a NumPy array. And so this .numpy is a shorthand thing we can do with TensorFlow to get it in NumPy format. So if we run these two cells again, let's see what happens. Okay, so now we have it in the form of a NumPy array. The one thing I do want to know, though, is what is the shape of the overall images? And oh, I guess we have one other issue, is that we did this in a list comprehension, but the surrounding data type is just a list right now. And if we want to make it also a NumPy array, we need to surround it with NP array. Okay, so run those two things again. Okay, we have 2,520 by 300 by 300 by 3. So it's 2,520 images with this shape. The one thing I would say, and this is really going to be problem dependent, is that we are working with these hands, and in my opinion, the colors don't really matter too much. So right now we have these 3 color channels, RGB, but in my opinion, we only really need 1 color channel because we're really looking at trying to find edges and whatnot. So I think if we have 3 color channels, we might kind of have more data than we actually need. So we're trying to reduce the number of things that the network has to learn. So ultimately, I think it would be nice to have this in grayscale. So we're going to do everything for the dimensions, for the first 2 dimensions. So we need to take all of these same points still. But for the last dimension, the color channel, we'll just take the first color channel. We'll just take that red color channel. And I think that's good. And so now let's see what we have. So now we don't have a color channel. That's cool. We'll have to do a little bit of additional processing. But let's now, in addition to train images, let's get train labels. And that will be NP array. This will be pretty similar. It'll be example label dot numpy. We can just take whatever label it is because it's just going to be a integer, as we looked at the data a little bit earlier in this tutorial. For example, in DS train. Okay, and I'm going to now just copy this code and also do the same thing for the test images. So I'm just going to change this out to test, change this out to test, and change this to test labels, and this to test. All right, let's load all of this. All right, so with this cell, we've now loaded everything in NumPy format. We need to do a little bit of a processing before we're ready to pass it onto our network. And there's a couple items here. So once again, we can see the shape. And if we wanted to check out the test images shape, it'll be pretty similar, except lower number of examples. All right, first thing is we need to reshape these. So I'm going to just say train images equals train images dot reshape. And if you remember what it was, I'm just going to comment this out just to see this again. We had 2520 by 300 by 300. So we're going to want to reshape this one to 2520 by 300 by 300 by 1. And the reason we have this 1 here is that whenever we use convolutional neural networks in Keras, we always have to have some sort of semblance of a color channel. And so by changing this to a 1, we don't change the number of values we have at all. We just are basically letting Keras know, hey, this is just a grayscale. These are just grayscale images. So we'll do that. And also now I need to just figure out my shape of the test images. 372. So I'll do the same line basically. But now we'll do 372 by 300 by 300 by 1. And this is 372. Okay, that now reshapes it. And we didn't get any error, so that's cool. Some other things we'll want to do here. So we've now reshaped it, and I think, let's see if I can do .info. Is that something? I think by .data type. Okay, this is good. This is uint8, so it's all integer values, and they're up to their RGB. I guess they're just R channel values from 0 to 255. When we're doing image classification, we like to work with float values, specifically between the range of 0 to 1. So one thing we're going to do is we're going to say train images, and we're going to say train images equals train images dot as type. And now it's going to be a float 32 instead of the int 8 that we had before. So this is just basically getting us ready to be able to convert it from the scale of 0 to 1 instead of 0 to 255. And so the last step we're going to do is say train images divide equal by 255. So the max value we can have is 255 because RGB values are between 0 and 255. So by doing this, we're scaling every value to be between 0 and 1. And this is just a good common practice that helps you classify, helps the basically network learn better than if you use the 0 to 255 values. You could leave it 0 to 255, but it's just ultimately, it's going to probably decrease your performance a bit. So it's a common step to normalize between 0 and 1, and that's what we're doing right here. I think that's all we need to do. The labels are all fine from before, so we don't need to do any additional processing to the labels. So we'll just rerun this cell. And now if we look at train images.data type, we'll see it's at float 32s. And if we actually wanted to like look at one of the values here, we'll see that all the values are between 0 and 1. And we could also even look at the shape here of a single example. 300 by 300 by 1. That looks all good. So I think that's good for the processing steps. All right, now let's go ahead and train our first neural network for this task. And I'm going to go through this pretty quickly because I've already covered kind of a lot of this in my previous neural network video. All right, to start off, let's define a model, and that will be a sequential model. And so in that, we're going to have to pass in some layers. So the first layer we'll pass in is keras.layers.dense. So as the kind of basic approach, we'll make it a fully connected neural network. So let's say that the first layer of the dense network is 512. When we're defining our first layer, we're going to want to define the input shape. So in our case now it's 300 by 300 by 1. And then we'll also want to define the activation. And a good one to use is RelU. Okay, that's our first layer. Our next layer is going to be another dense layer. So we'll do keras.layers.dense. And we'll make this one a little bit smaller. So how about we do 256 here. And then make the activation another RelU. And then finally, let's define our output layer. And so the output layer is going to be the same size as you have labels that you're trying to classify between. So in our case, this will be a dense layer of 3 because we have rock, paper, and scissors. And let's also define a activation layer for our output. And when we're doing classification and just identifying one label, softmax is a good choice here. All right, that looks good. So then we're going to have to set up the loss function for this. So we'll do model.compile. We'll pass in the atom optimizer. We will use for our loss function, we will use keras.losses.sparse categorical cross entropy. And then finally, we will pass in our metrics, and that will just be accuracy. Okay, so we have our loss function set up. And finally, we need to fit our data to the model. So model.fit, we'll do train images, train labels, and then we'll do epochs, let's say, equal 5, and batch size equals 32. Run that. Input shape is not defined. Oh. Equals 300 by 300 by 1. Okay, come on. All right, so we got an issue. Invalid incompatible shapes 32 by 1 versus 32, 300, 300. And ultimately, I think our issue here is because we're passing in an input shape, and this is kind of a complex, this is an actual image and it has a complex dimensionality. So instead of doing this, what we're gonna do, and this is usually what you're going to do if you're trying to use a fully connected layer for images. We're going to do keras.layers. We're going to add one more layer, and this is going to be called a flattened layer. And basically what this does is it transforms that 300 by 300 image into just a single column, which would probably be of dimension 90,000. So that's what we're doing with that layer. So now I think we should be able to run this training step. And it's running, and because this takes a little while, I'm going to just kind of speed through this section, and I'll do that probably in general. All right, it finished. And looking at our results, you see that after the last epoch, we had about 90% accuracy. So you might be like, wow, like this was so easy. We've already classified these hands, these rock, paper, scissors hands, like very well. Well, I think though it's pretty telling if we try to do a model.evaluate on the test images and the test labels. This will tell us how well our model generalizes to unseen data. And so if this is also high, then like we're golden, but I don't think it will be. Yeah, and as you see here, it got 50% on the test data. So there's a big disconnect. We were able to classify 90% of the training examples properly, but only 50% of the test. So it's not doing a very well job on the test data. And the big disconnect here is that we are using this fully connected layer for these 300 by 300 images. And so that's a total of 90,000 like single, I guess, pixels that we are connecting to the next layer of our network. And ultimately, we don't have we're putting too much importance in those little single pixels. So what's happening here is that we're overfitting to our training data. And we're not really learning good patterns because, as you see in our test data, we got 50%. So ultimately, this is what's going to lead us to want to use convolutional neural networks to kind of get a more sense of generalizable features within our rock, paper, scissors images. So that's what we're going to do for our next network. I'm not going to go through the details of a convolutional network in great depth, but basically we can think of all of our images as a grid. And before we are using each pixel to feed into our network, now within our grid image, we are passing over a smaller grid across the entire image. And basically with these smaller grids that we're passing on the entire image, these convolutions we're performing, we're learning features that occupy a little bit more space. And as we think about it, like images, there's so much variance in how they are. So we need to like at a higher level be able to pick up on those features. So that's why we're going to pass these smaller grids over our bigger grid to hopefully pull out general features in our images. All right, and so we're going to, again, start this off by defining a sequential model. And this time what we're going to do is our first layer is going to be keras.layers.conv for convolution and 2D because this is a 2D image. And then we have to pass in the appropriate parameters. So if we look at our Google Colab, we need to first pass in filters. So this is basically how many different smaller grids we're going to pass on top of our image. And each of these smaller grids is going to have a different kind of shape and try to find a different pattern. I'll link to some resources that can explain this in more depth. It's basically how many times we're passing over a smaller grid on our image. So we're going to say this is 64 as just a kind of a safe first answer. Our kernel size, this is how big our smaller grid is. So if I said 3 and I didn't pass in any other parameters, this would assume 3 by 3. I think you could also pass in, if you wanted to have a different sized, the X and Y direction, you could do like 3 by 6 and that would be a rectangular. That'd be a rectangular kernel size. So we'll say, let's just say 3 to start off. And we'll leave the strides at 1 to 1. That just means it'll move 1 every time. So it's going to be a sliding window of 3 by 3. All right. And how about we'll give that an activation of relu, just like we have been. And now we actually do need to define the input shape. And this time it will expect a multi-dimensional shape. So we can do 300 by 300 by 1. That's totally fine. Now, I'm going to just pass in another convolutional layer. So we're going to do another 2D convolution. This time we're going to make it a little bit smaller. We'll say 32 filters with kernel size of 3. Activation equals relu. And all right, I think that's good. We have 2 convolutional layers. And now we're going to want to pass this to a kind of the output layer. And to do that, we first need to flatten the output of all these convolutions. So we're going to pass another flatten layer. Keras.layers.flatten. And then we'll, just like in the last case, we'll do keras.layers.dense. And this is our output layer. So we'll do 3 with an activation of softmax. Cool. That looks good. And we're just going to go ahead and copy our loss function from above. Right. And let's go ahead and try to train this. It's working, but it seems to be going really, really slow. Like too slow to, really, really slow. One insight here, and this is something, it might have been annoying that I haven't told you already, but within Google Colab, we can actually run on a GPU if we want to. So like right now it shows that like this single epoch will take 10 minutes and it's not ideal. So what we're going to do is we're going to stop this real quick if I can. Stop. Okay. Oh no, stop. I stopped it, but then I tried again. All right, so we're going to real quick just change our runtime. So if you go to runtime and then change runtime type, we're going to use a GPU hardware accelerator. And really only use a GPU if you need one, as they kind of say. So we're going to save that. We're gonna go back, and now basically we need to rerun everything because it's using a different hardware. So I'm just gonna run all the cells that are relevant here. And we don't have to run this one again because that's not what we're focused on right now. We'll run this one again once everything else is done. Let's just let these execute. All right, and now let's run our convolutional neural net. Last time it said it was going to take like 10 minutes to run a single epoch. Let's see how well it runs with the GPU. And look at that. From what it was taking about 10 minutes, we've now run a single epoch in about 10 seconds. So that's really cool. Look at this. It's like really performing well now that we've used that convolutional layer on top. And wow, it's at the last layer here, it's predicting all of the training utterances properly. But, you know, the ultimate test is it doesn't matter if we can do really well on training data. That has no meaning unless we can do well on test data. So we're going to do model.evaluate, test images, and test labels. And let's see how we do. Jeez, we actually did worse than we did before with the fully connected approach. So obviously we overfit again. So let's see how we can improve this convolutional approach and hopefully avoid our overfitting problem. All right, so now we're going to define another cell. I'm just going to call this a better convolutional network. All right, how can we improve this network that obviously overfit? I'm going to just go ahead and copy this into our new cell. No need to start from scratch. But let's look at this. What is the main issue that we're having and why are we overfitting? And this is definitely not obvious unless you've kind of started to work with image classification a bit. I would say the problem kind of boils down to the fact that we don't have that many training examples. You know, we have under 3,000 training examples, or yeah, I forget the exact number. Yeah, I think we have 2,520 training examples. So that's not that many in the grand scheme of things. And also the other real big issue that I see here is that our images are 300 by 300 by 1, but our kernel size here, the small grid that we're passing on top of the image when we're doing the convolution, is just 3 by 3. So it's still like a really small rectangle we're passing on top of the big rectangle. So what we're ultimately going to do, and like obviously like if we're thinking about our image, we don't need high resolution images. As long as like the base features are there, we should be good. So ultimately what we want to do here is reduce the size of this input image before we start performing the convolutions on it. So what we're going to do is we're going to add an average pooling layer. So keras.layers.average, I think it's average pooling 2D. That sounds good to me. And what are our options here is pool size. We'll say our pool size is going to be 6. We can pass in if it's a square, we can just pass in one coordinate again, but we could also pass in multiple coordinates. So, and then our stride. Our stride is how far, if we have a 6 by 6 box, our stride is how much we move that box each time we do an average. So I'm going to say that this is 3. So basically what we're doing here in this layer is that as we pass it, and we're going to also have to pass in the input shape here. So what we're basically doing is that we have this 300 by 300 input image, and what we're doing is basically passing a 6 by 6 box on top of that image, and every time we do that, we're averaging all the pixels, and that's our kind of new representation of that box. And instead of moving the box entirely over, we're moving the box 3. So every 2 times we move the box, we are at a like basically new location. So you basically have this, and this, and this, and this second time you move that box here, kind of covering new squares, I guess, from the first time you did it. So I guess the better way to say this is that each pixel is counted twice in this representation. But basically, we're going to boil this down. If we have 6 and we're moving on top of it, it's going to boil this down from 300 to 300 to, I believe, if I'm not mistaken, 100 by 100 as the new kind of input. And you could reduce this further if you wanted to. If we did 6 by 6 here with a stride of 6, I think this would reduce it down to 50 by 50. So that's another thing to try, but I want to count each pixel twice here. And then we'll feed this now into our convolutional network. So this is basically just the image with, instead of size 300 by 300, after this layer, it's 100 by 100. And let's see what happens to our network when we just do that reduction in image size. So it still like basically classifies the test data very well, but let's see what happens when we evaluate it. So test images, test labels. I want to do better than last time. Okay. 56%. I mean, that's definitely better. I think we can still do better here. And I would say what our issues here are now, and this is kind of comes with practice, and I wouldn't notice these things unless I really looked at this for a while, and I have looked at this example before doing this, so I have more of an intuition I would coming into this exercise cold. But we have a lot here. Another very common thing in convolutional neural nets is to do some max pooling. And this is basically for the same reason, is we don't want to take too many dimensions when we're doing these things. So max pool 2D is going to basically do the similar thing as an average pool, but now we're going to pass over our output with 2x2 grids and just take the max pixel in every 2x2 grid. And this time we're moving the 2x2 grid 2 every time. So each pixel is only counted once, but we're just taking the max pixel value from each of those. So let's see what happens if we add that. And I screwed something up. Oh, Keras.layers. All right, how are we doing? All right, 66% accuracy on the test data. That's a lot better. And it's ultimately because we're reducing the size of things, and basically individual pixels don't have as much weight anymore. So it's a smaller input space, smaller parameter size, so that our model should generalize more. But there's one major thing that I'm thinking of that we can do to probably help things out, and that is to use dropout. So one of our main issues with our training examples is that we don't have many. And so what dropout will do is that after we're done with the max pool 2D layer, we're going to basically cut out 50% of the connections. So as we train things, 50% of the connections at this layer are going to be dropped out. And ultimately, the epochs will be more effective because the data will be kind of more interesting because these things are getting dropped out randomly. So each of the individual connections will kind of have to generalize more and be able to handle more variation. So this is going to kind of help us simulate having more training examples by using this dropout layer. And 50% is a good, it's kind of in research, the common value to go to with this dropout layer. So let's try this. And thankfully we're on the GPU, so everything's going really fast. So we went from 66 in the last layer. Okay, and we're about the same, 65%. Didn't seem to help too much. The last thing that I'm going to recommend doing, and this is something that you just really play around with, but we're going to add another dense layer here. So instead of going from everything to 3, we're going to try to learn an intermediary representation before we actually do the output. So we're hoping that maybe this layer can capture some higher level information and boil it down to the 3 better than just passing all of the outputs of the convolution and the dropout and everything straight to our classification layer. So we'll make this 128. We'll see what happens if we use ReLU activation, comma here. All right, moment of truth. All right, look at that. 70% accuracy. That's pretty good on the test data, on unseen data. I'm pretty happy with that. So I think as far as on your own, you could tune these values and play around with adding more values and whatnot. Maybe you'll get better results. But our next and final basically step of this example will be to look at automatically tuning the values in this network and maybe adding more layers to see if we can get even better test accuracy than 69%. To automatically tune our network, we're going to use a tool called Kerastuner. And it just does a lot of the work for us and makes it very easy to find the best parameters for our network. So I think the easiest way to learn about Kerastuner is to go to the Kerastuner website. I'll link this in the description. But here we are. So to start off, we need to install it. So we can use pip install -u Kerastuner. So I'll just copy that command and I'll run that with my notebook. And while that's going, I think we can look back at that documentation and just read through usage the basics. And I think it already kind of starts making things clear. So here we have this build model with this hyperparameter variable that we're passing through. And as we see this is used, was basically we're defining a sequential model. And this is a slightly different format than we defined ours. So we'll have to kind of refactor our current network a little bit. But we are, basically in this step they're adding a dense layer, a fully connected layer. And this time the big difference is that the number of units for that single layer is defined as a variable. Like it can be different values. And this is what we're testing and playing around with. So it's saying basically that we want to try the min value of 32, a max value of 512 for this layer, and a step size of 32. So behind the scenes, this build model and the Kerastuner will test the numbers from 32 to 512, skipping every 32 units for this dense layer. And we can do this for a bunch of things. And we don't just have to use this int command, there's other commands. So as you see down here, they're playing around with what learning rate should we use. So it's in the Atom Optimizer, it's using a choice of the learning rate. So it's trying these three values at random with the variability up here as well. So it's allowing us to test different combinations of things very easily. So let's go ahead and just start writing this into our code. So the first step is going to be to take our network from up here and rewrite it kind of in that format that they were using. So if we look back at that, so the first step will be to import the random search. We've already imported the Keras and the layers. We want to import random search, and then we're going to define that build model with that hyperparameter variable being passed in. And I've actually already done this just to speed it up a little bit, the conversion to this different format. So our new model will look something like this. So this is the same exact model from above, but now I just wrote it with this different syntax where we define the model as just the sequential and we add to that. But same exact model. And we're going to have to also add in the loss function again to our function. And then finally, we will return the model from the function. That's really all we have to do, but now we can decide if we want to play around with variables. So let's go back to the documentation. We have, next step looks like is defining this tuner. So I'll just copy this in. So it's calling the build model function. The objective is the validation accuracy. So how well does it do on our test set? Max trials right now is set to 5. I'm not quite sure what executions per trial is. I think that's how much times it's trying the different combination of parameters because there's some randomness involved. I'm not going to keep that for now. And then you can also choose where you save these results. By default, it'll choose something. So I'm going to just probably get rid of these directory and project names for now, but know that you could set those if you want to save it in a certain spot. All right, that's good. And then finally, once we have now defined our tuner, we need to do a tuner.search, and we need to pass in some parameters. So we need to pass in first our X and Y, so our train images, our train labels, and then we need to pass in what we're trying to optimize this network for. And so that's going to be our validation data. And that's going to be equal to the test images and the test labels. Then we can also set stuff like epochs. So I'm going to say 10 epochs now and batch size of 32. Cool. And now the big difference is we need to now choose some of these values to play around and try to optimize. So I'm going to just, as an easy example, play around with this dense layer right here at the end. So let's see what our options are. We can use this hp.choice. I think that will be helpful. Or we could probably use this hp.int, which chooses random int values. Either of these options is fine. I think it's sometimes easier to use this hp.choice just to kind of limit the number of things I try. So I'm going to go ahead and do that. So I'm going to set this, instead of just 128, it's going to be now hp.choice. hp.choice. And we now need to pass in a name whenever we're using one of these. So this is going to be, I'm just going to call it dense layer. And now what do we want for our choices? Well, our initial was 128, so we can keep that in there. But how about we also try 64, maybe 256, maybe 512, maybe 1024. So now we have 5 different options here. And what we can do is go ahead and now run this search. And we have 5 options, so max trials 5 is good, but if we had more combinations of things, you might want to bump up this max trials value to something like 32. It'll run random combinations of the parameters you're trying to use until it hits 32 or until all of the trials are exhausted. So in our case, we only have 5 different things it can choose from. So it should really just run 5 trials. So this is a very simple example of using the tuner, and let's see how things work. And note the tuner can take a while to run, so just be wary of that. Because we're only testing 5 different things, it shouldn't be too bad in our case, but that is something to note. All right, awesome. Everything executed. So everything has run. We've now played around with the different number of parameters here. So let's see some results. One of the best things to do first, I guess, is you can actually get the best model that was found during that by doing tuner.getBestModels. Oh no, not hyperparameter. Models. And then grab the 0th index, so that's going to be the top model. And now best model is actually equal to tuner.get. It's get best models like this. It's a function. So now best model is set to the top thing that the tuner found, and we can actually do best model.evaluate train images, or sorry, test images, test labels, and see how well it does on that data. And look at that. So it got 73% accuracy. So that was like a 4% increase just by figuring out a better value to use for this last layer here. And one thing to note too is that this get best models will not only select the best value that it found here, but it'll also select the parameter weights from the best performing epoch during the training. So it did give us a boost in accuracy there. We can also do some other stuff here. One thing we could do is see what actual parameters that best model is using. So summary, we can do bestmodel.summary. And that shows us that it found that 1024 for that last layer did the best there. So that's something to note. And it also gives us the kind of info on the other layers that we're using in the network. That's pretty cool. You can also do tuner.results summary to just get some high level results on how those trials went. So you can see kind of scores from each one of those combinations of layers that we used. All right, so that's the basics of using this search. But I think really playing around with this, I was able to, I think, get up to like 81% accuracy on the test data. And to do that, I added some additional things. So I like played around with how many convolutional layers we used and how many filters. So that would look something like this. So for I in range hp.int, and now this is going to be convolution, I'm going to say con layer, how many convolutional layers we have. And that's going to be, let's say, between 0, the min value is 0, max value, let's say, is equal to 3. And then you can also, with this one, set a step size, how many times it skips. But its default is 1, so I'm going to leave that. And basically what we could do here is add, we're going to delete this one. Basically, in our tuner, we can decide how many of these convolutional layers to add. And additionally, we could even like play around with making this a variable parameter. So I'm going to say f layer. So just bear with me for a sec. Filters. Basically, I'm going to, in the convolutional layer, I'm going to play around with how many filters we use. So hp.choice. And I'm going to say we could use maybe 16, 32, or 64. And complete that. And then we'll still use a kernel size of 3. And we'll still use activation rel u. But basically now what we're doing, if we were to rerun the search with this, is we're deciding whether we add 0 convolutional layers or up to 3 convolutional layers. And within each convolutional layers, we're also playing around with the number of filters that we use by using this hp.choice. So you can get really creative with this. And as I mentioned, if you play around with this enough, I think I got up to like 82% accuracy on this test set by just playing around with these values. So you could rerun this and play around with things. It might take a little bit of time to really run this. And also one thing to note is the tuner, I think by default, if it sees you have results already saved, you might have to either delete your results or save it in a different directory here. Just because it doesn't want to run this time-intensive search process again if you've already gotten results. So it's kind of a safety thing that Kerastuner does. And also I'll link to some other videos. I saw one by Centex and one by Krish Naik that did good jobs explaining this Kerastuner as well. So I'll link to those. But that's all we're going to cover for the Kerastuner. All right, to end this video, we're going to rapid fire go through some things that will be helpful as you try to transition the knowledge you might have gained in this video to other projects. So the first thing that's useful is how do we save and load our models. So we can do that by just doing, let's grab the best model from the tuning step. We can do best model.save, and we could just call this like in our current directory, my model. And so this would save all the parameters in that model. And then you could reload it with .load. So like, I'll just call this loaded model equals keras.models.load and load model. And then we just need to do that same path. So my model. And one thing to note is that with Google Colab, I don't think that anything will persist. So anything you save here won't stay saved next time you run this. But if you were to do this locally on your machine, you would have this model saved there. So as you can see, I could do loaded model.evaluate. And get the same results as before. So that's something useful to know. Another thing that is useful as you try to carry this into your own projects is how do we plot NumPy arrays as images? How do we see those images from the NumPy? So I'm going to say plot image from NumPy array. This is something useful we'll want to do. And it's actually pretty easy to do this. So let's say we want to plot one of our train images. So train images 0.shape I'm going to just look at real quick. So that's 300 by 300 by 1. What we can do is just go ahead and do, we need to import matplotlib, which we might have already done, maybe not. Let's see. Plot.show. Yeah, I think we already did import matplotlib earlier in this video. So using matplotlib, we can do plot.imageShow of train images 0. And let's see what happens. Invalid shape for image data. So it doesn't like the 300 by 300 by 1. But if we pass in the color map and just let it know that we're only using grays here, I think it should be fine. Okay, it still doesn't like that. I think it's the weirdness of having this extra 1 here. So what we can do is it just need it to be 300 by 300 and not have any color channel. So we're going to go ahead and do image equals train images 0 dot reshape 300 300, and now we'll try to just plot that image. And as you can see, we've now plotted the image in grayscale. What we could also do, if let's say we wanted to plot it in RGB scale, we could go ahead and just kind of looking back from the initial thing we did. So this is just going to be RGB test, I'm going to say, or RGB image equals numpy.array. And this is just copying from earlier example, image dot numpy for example in ds train. I'm going to say dot take 1. This will only take run it for 1 image, so it'll just go a lot quicker. And this is RGB images because that's going to be an array. So RGB image equals RGB images 0. And now I could also do plot image show RGB image. And now I don't need a color map because this is RGB scale. And look at that. Now we got the image with color. And just to show you what RGB image is, dot shape. That is 300 by 300 by 3. So that's plotting images from a NumPy array. The other thing you might want to do is how do we load in a PNG image or a JPEG image and actually convert that to NumPy? So that's another useful thing. So convert PNG/JPEG images to NumPy format. That's also useful. And we can do this very easily with a library called image.io. So import image.io. And then what we're going to do is image equals image.io.imageRead. And now you would pass in the path. So this would be path to image.png. But if you don't have any images stored, or you could also just read images directly from the internet. So if I just went to Wikipedia, let's say, and looked up Boston, that's where I'm from, I could just take a picture from Wikipedia. So, here is our Capitol building. So I'm going to copy the image address. So if I go to that address, you see we have that image. So I'm going to just copy this address. And one thing that's pretty cool is that in the image read method, you can actually just pass in URLs. If it works. And now we have that Boston image loaded in through the command here. I can go ahead and plot.image show the image just to show you that we've read it in. And as you see, it's that Boston image. And then the final thing is we want to convert it to NumPy. So what we would do there is let's just print out the type of image. It's an image.io file, but to convert it to NumPy, we can just do image.np equals np.asArray and just pass in the image. And now if we print image np.shape or something like that, we'll see the dimensions of that image. And basically all of our image information is now stored in this image np variable. So you could imagine using this on your own set of images to build a neural network from scratch. So it's another useful thing to know. All right, with that, we're going to end this video here. Hopefully you guys enjoyed this one. Hopefully you learned something. In the description of this video, I'll link to some resources to learn more about convolutional neural nets, because I think, particularly with convolutional neural networks, it's very useful to kind of read some literature about them to kind of ultimately use them as effectively as possible. So check the description for that. If you did enjoy this video, it'd mean a lot to me if you throw it a thumbs up. And if you haven't already, please subscribe to the channel. Also, check me out on the other socials, Instagram and Twitter. I post probably more frequently in those places, so if you want to stay up to date with everything I'm doing, check there. Anyways, guys, it's been fun. Thank you for watching. Until next time, peace out.